take a look at the idea of taking derivatives and integrals of vector functions. But first, we'll start with the idea of taking a derivative. So let's start off and say, let's let r of t, be a vector function. Then dr dt equals r prime of t, which is equal to the limit as h goes to 0 of r of t plus h minus r of t divided by h. Now, see if the limit exists. Now, this is the same definition of a derivative that we introduced back in Calc 1. It's the exact same thing. We're just now going to be using it with vector functions. So let's take a look at a theorem, because this theorem will actually tell us how to go about this. If r of t equals f of t, g of t, h of t, which obviously equals f of ti plus g of tj plus h of tk, where all of f, g, and h are all differentiable functions. Then r prime of t, the first derivative of the vector function, is equal to the first derivative of f of t, first derivative of g of t, the first derivative of h of t, which is obviously can be written as f prime of ti plus g prime of tj plus h prime of tk. Now, let's just take a moment and walk through a quick little proof here. Now, r prime of t, by definition, and I'm going to go to delta t's, although I could do this with h's, but I'm going to go to delta t's. We'll take the limit as delta t goes to 0 of r of t plus delta t minus r of t over delta t. Well, obviously, these are functions, which is equal to the limit as delta t goes to 0 of f of t plus delta t minus f of t, g of t plus delta t minus g of t, h of t plus delta t minus h of t, and I need to put my delta t in there, so let's just divide the whole thing by delta t, which is equal to the limit as delta t goes to 0 of f of t plus delta t minus f of t over delta ti plus the limit as delta t goes to 0 of g of t plus delta t minus g of t over delta t j well, I hope I fit this other guy in here, plus, start writing smaller, the limit as delta t goes to 0 of h of t plus delta t minus h of t over delta t, and we put k in there. Well, that is equal to f prime of t I plus g prime of t j plus h prime of t k, which is obviously back in the component form, f prime of t g prime of t h prime of t. Okay, r prime of t, well, that's the end of the proof, in case you don't recognize that. R prime of t is the tangent vector to the curve defined by the vector curve r of t at the point P, provided, this is supposed to be a P for the point P, provided r prime of t exists and is not the zero vector. Now, the tangent line to the curve defined by r of t, let's see, the tangent line to the curve defined by r prime of t at P is defined to be, now, and this is very important to kind of understand, to comprehend how we're going to interpret this tangent, is defined to be the line that's through P. So it's a line that goes through point P, and it's parallel to the tangent vector r prime of t. Now think about what this just got done saying, because this is really important here. The tangent line to the curve defined by r of t at P. So I have some space curve, and at a specific point P that's on that curve, the line tangent to it is defined to be the line that passes through the point P. That makes sense. And it's parallel to the tangent vector. Okay, that's telling you that the tangent vector itself is really a directional vector. So the tangent line goes through the point, and it's parallel to r prime of t. So r prime of t, we start thinking about how we write lines, equations of lines, in vector equations of lines. It's based on a known point and a directional vector. So this r prime of t, the derivative, the first derivative of our vector function, is actually a directional vector. Now the unit tangent vector is, we would define it the same way we do any other unit vector. So I'm going to have r prime of t divided by, you guessed it, the magnitude of r prime of t. That's what makes a unit vector. So when we have a need for a unit vector, a unit tangent vector, that's exactly how we would go about it. Now, let's take a look at a quick example here. Now, given r of t equals cosine t, sine t, and 2t, find the first derivative and the unit tangent vector at t equals 3 pi over 4. Well, r prime of t is going to be equal to d dt cosine of t, d dt sine t, d dt 2t, which is going to be negative sine t, cosine t, 2. So that is my tangent vector. Now, specifically at 3 pi over 4, what I need to do is I need to find r prime of 3 pi over 4, which is equal to negative sine of 3 pi over 4 cosine 3 pi over 4, 2. And these are, I probably shouldn't write quite so fast, those are parentheses. This is, I'm writing in vector component form, in case you didn't quite catch that. So that's going to be sine of 3 pi over 4 is root 2 over 2, but the negative of it is going to be negative root 2 over 2. Cosine of 3 pi over 4 is a negative root 2 over 2, and of course 2 is just 2. So there's my tangent vector at that specific point. So if I'm going to go ahead and find the unit tangent vector, I'm going to write this as, no, I'm just going to leave it like that. Negative root 2 over 2, negative root 2 over 2, and 2. There's my vector. Divided by the magnitude of that vector. That's going to be the square root of negative root 2 over 2 squared plus square root of negative, plus negative root 2 over 2 squared plus, that is 2 right there, plus 2 squared. And that is going to give me, I'm going to bring this out. This is, it's going to be 2 over 4, so it's a half, and 4. That's 5. This is 1 over root 5, so it's going to be 1 over root 5 times the vector negative root 2 over 2, negative root 2 over 2, 2. Now, if you want to write that using the basis vectors or whatever, it doesn't really matter. But there's the unit tangent vector. And this is the tangent vector at 3 pi over 4. And again, this is the unit tangent vector also at 3 pi over 4.